So today we're going to talk about quaternions, only we're going to do it from the perspective of the famous mathematician William Rowan Hamilton. Okay, Hamilton is the one that invented quaternions. He discovered them, he defined them, and so we're going to be demystifying quaternions from the perspective of Hamilton himself. This video was actually inspired by this paper, which was recently published in the International Journal of Engineering Research and Development, called The Evolution of the Complex Plane to the Quaternion Coordinate System to the Transspatial Geometry. Okay, so I'll explain to you in a minute why this paper here is the muse, I guess I could say, for this video. But before I continue with Hamilton's quaternions, I want to talk a little bit about this guy here. Okay, so this is a mathematical statement that I see written by many people. Okay, it's not just one person or two people. I see this video, I see this mathematical statement written in videos and in scientific papers. And to me, this mathematical statement is not correct. And the reason I don't think it's correct is because the square root of -1 has two solutions, I, positive I, and negative I. Okay, so this mathematical statement is not true in the mathematical sense. So in the mathematical truth of a mathematical statement, in the mathematical rigor of a mathematical statement, this statement is simply not true. Okay, so I is not equal to the square root of -1 because the square root of -1 is equal to plus and minus I. So as a mathematical statement, this mathematical statement is not mathematically true. Okay, so when people write this, it really bothers me. I think maybe I'm a little OCD about this, and so it really bothers me when I see this in a video or in a paper. Unfortunately, it's actually very common for people to make this assumption, for people to make this mistake. I'm calling it a mistake. It's only a mistake in notation. Okay, it's a mistake in notation in that you should be writing the square root of -1 is equal to plus I and minus I. So it is a notational problem, but it is also a conceptual problem, which is a cause for confusion. Okay, so I want to remove the confusion from the language by doing things in a very specific way. A lot of mathematicians tend to skip steps, even though we're told in school. I remember I was taught in school in mathematics that in order to get a perfect mark on a question, I have to show all my steps. And so a lot of times you'll see something like this where a lot of assumptions were made. So basically what she's doing here is she is taking the square root of -9, okay, and she is decoupling the positive 9. She's taking the positive 9 out of the square root and saying that that is equal to plus or minus 3. Therefore, I is equal to the square root of -1 because we know that the answer to the question is plus or minus 3i, okay? So, but what I'm going to show you my line of thinking, and you're going to see that she actually skipped a step here in order to come to this conclusion. Okay, so in order to solve the square root of -9, what Kathy did, and this is what she said she did in the video, so I know she did this, is she decoupled the positive 9 from the square root and took the square root of that separately and left the -1, the square root of -1, okay? So then she wrote, she went straight from this to, so the square root of 9 is plus or minus 3, therefore the square root of -1 must equal I, because we know the answer has to be plus 3i and minus 3i. Okay, but here's what I would do instead. What I would do instead is I would do the same decoupling that she did, and then say the square root of plus 9 is plus or minus 3, and the square root of -1 is plus or minus I. Okay, then I would map all these out. So 3 times I is 3, so yeah, you would do plus 3 and plus I is one solution, plus 3 and minus I is one solution, minus 3 times plus I is a solution, and minus 3 times minus I is a solution. And this simplifies to plus 3I and minus 3I, which is the same solution that Kathy wrote down here. Only I believe that her line of thinking is wrong in that the assumption that the square root of minus 1 must be equal to I, or sorry, I must be equal to the square root of 1 because of her logic here. Okay, so with my logic, I can derive the same formula, get the same answer. The square root of minus 9 has two solutions, plus 3I and minus 3I. Okay, but I take it a little further. Okay, so the square root of minus 9, I skip all these steps now. I don't want to show them because I want to show you how beautiful this is when you don't show all the junk. Okay, so the square root of minus 9 is plus 3I and minus 3I. And under the hood in 2 by 2 matrix form, okay, plus 3I is this matrix here, and minus 3I is this matrix here. Okay, so what I've done was I've closed the loop on the confusion, and I've given the square root of minus 9 two 2 by 2 matrix solutions, which are which I can write down, and I can now do calculations using these matrices. Okay, and so when I guess the point I'm trying to make is when you try to do this algebraically, okay, let's go back to here. When you try to do this more algebraically, trying to stay in the context of the one-dimensional 3D numbers and not expanding your mind to the fact that we can have two-dimensional numbers. These are called complex numbers. Okay, when you don't do that, you end up making maybe wrong assumptions here. They're assuming that I is equal to the square root of negative 1, and we know that that is not true because the square root of any number, including negative numbers, have two solutions, I and minus I. I also want to point out that this is not the rule that Hamilton wrote in his paper. This is not the rule that Hamilton or Euler used in their papers. Okay, what they write, they're very specific to write I squared is equal to minus 1 when they're talking about imaginary numbers. So whenever they invoke imaginary numbers, the imaginary unit I, they always write where I squared is equal to minus 1. They never write where I is equal to the square root of negative 1 because they were smart, they're good mathematicians, and they knew that this mathematical statement wasn't 100% rigorously true, and so they were very careful to write I squared is equal to negative 1, as you will see when we review Hamilton's paper. And this is the reason why I'm invoking this paper, because this is an example of an officially published paper where they're using I is equal to the square root of negative 1 instead of I squared equals minus 1 as Hamilton did to describe the rules of imaginary numbers. Okay, so it says, but given that a set of real numbers represented by A is a subset of the complex numbers A plus IB, in which I is equal to the square root of negative 1, and A and B are real numbers. Okay, so he should here have said where I squared is equal to negative 1 like Hamilton did, and this really bothers me. The only reason this bothers me with this paper is because the author of this paper is using this statement here as the foundation for his thesis. Okay, so he's actually using the statement here. He actually goes on, I'll show you a little later, where he actually says I equals J equals K equals square root of negative 1. So he's using this also as to define the unit vectors of the quaternions. And if this statement is wrong, if I equals the square root of negative 1 is wrong, then I equals J equals K equals the square root of negative 1 is also wrong for the same reasons as I explained earlier. But more importantly, this is not what Hamilton wrote. Okay, this is not what Hamilton wrote. These are not the rules of quaternions that Hamilton wrote down. What Hamilton wrote: I squared equals j squared equals k squared equals minus 1. Okay, in his paper, he writes right here, he writes that when you write an expression of the form x plus iy, in which I squared equals minus 1. He does not write I equals the square root of negative 1 for a good reason, because I equals square root of negative 1 is not a mathematically rigorous statement. It is not a statement that is true. I squared equals minus 1 is a true mathematical statement. It is also true that minus I squared is also equal to minus 1. Okay, so both Euler and Hamilton were very rigorous about writing I squared equals minus 1. Now, I think there's other parts in this paper. So here again, he's writing I squared equals j squared equals k squared equals minus 1. Here he's also writing I squared equals minus 1. Hamilton is very careful to not write I equals the square root of negative 1. He always writes I squared equals minus 1 for a reason, because this is a true mathematical statement. I was actually in an email conversation with the author of this paper, and I was trying to convince him not to write the statement I is equal to the square root of negative 1. In fact, I was trying to convince him, I was trying to convince him that the statement I equals j equals k equals the square root of minus 1 was an incorrect mathematical statement, and I was trying to convince him not to use that as the foundation for his hypothesis. And so he came back with, luckily for all of us, and particularly for your own computer graphics programming profession, you were not around when Hamilton came up with this idea in 1843, because you would have rejected the foundation of the very concept of quaternions. Now, I thought this was kind of a funny statement. It was obviously a little bit of a dig, because I am a computer scientist and I do use quaternions, and I absolutely do not reject the foundation of the very concept of quaternions, which is this statement right here. Okay, this statement I squared equals j squared equals k squared equals minus 1 is what Hamilton wrote. In fact, what he actually wrote was I squared equals j squared equals k squared equals ijk equals minus 1, and he carved it into the, I'm not sure how to say that, but I think it's loosely called the Broom Bridge, as he was passing by the bridge and he had his revelation and he carved it into the bridge. So this is the foundation of Hamilton's quaternions, okay? And this is the foundation that I accept 100%, and I use it perfectly fine in my computer graphics program without any problems whatsoever. So the other problem I have with Andre's paper is he is trying to use this statement, this incorrect mathematical statement, I equals j equals k equals the square root of negative 1, as a unit vector set. Okay, so I and j and k are not unit vectors. They are not vectors. The square root of negative 1 is not a vector, as I showed you earlier. The square root of negative 1 is I and minus I, and I and minus I form rotation matrices. Okay, they are 90-degree rotations in the complex plane. So rotations are not vectors, and so I equals j equals k equals the square root of negative 1 as a unit vector set is incorrect. And this is what I meant where when you make an incorrect mathematical statement, you may make an incorrect mathematical interpretation of that statement. I equals j equals k equals minus 1 it definitely does not form a unit vector set. I, j, and k are imaginary units. I agree with that. They are imaginary units, and in the quaternion space, I guess you could say. But they definitely do not form a unit vector set. And so here you can see that he is trying to use the unit vectors. So he's trying to use ijk equals square root minus 1 as the unit vectors. And this is absolutely not true. This is not, I, j, and k are not unit vectors. And when you use I, j, and k as unit vectors for some theory, then your theory is going to have a not a solid foundation. Okay, so basically in computer science we used to have a saying, garbage in, garbage out. Okay, so in this paper, anything that this person uses as an interpretation, if he uses this to make an interpretation about electromagnetism or about LC circuits, as he does in this paper, you are going to get the wrong interpretation. Okay, it might sound interesting. There's lots of really good buzzwords in this paper that, you know, made me want to read it. It sounds really interesting, but the foundation of his hypothesis is ill-founded. And so this is why I think it's really important that we understand this is not what Hamilton wrote. What Hamilton wrote was I squared equals j squared equals k squared equals ijk equals minus 1. He wrote this and he meant this. I also want to make one more comment about Andre's paper before I move on to Hamilton's paper. In this figure here, the quaternion rules that he's writing here for the j times k equals k times j equals minus 1. These are not the quaternion rules that Hamilton came up with. He's making up his own rules here for some reason. And so again, I'm going to say garbage in, garbage out. When you interpret I, j, and k as some sort of unit vector, you are going to get the wrong quaternion rules. These are not the quaternion rules. So he's just making this up as far as I'm concerned. And maybe he thought it was an interesting idea at the time, but it might be an interesting idea, but it is not a good idea to go against Hamilton and write things that Hamilton didn't write and interpret the I, j, and k in a way that Hamilton didn't intend. Okay, so peer review is broken. Peer review is broken, in my opinion. I'm not sure how much scrutiny this paper went through, but all I have to say is peer review is broken. So now we're going to go back to a time where peer review wasn't broken. Okay, so here in this paper on quaternions, we have Hamilton starting out with let an expression of the form Q equals W plus IX plus JY plus KZ be called a quaternion when W, X, Y, and Z, which shall be called the four constituents of the quaternion, denoted any real quantities. So W, X, and Y, and Z can be real quantities, positive or negative or null. But the I, J, and K are symbols of three imaginary quantities, which we shall call imaginary units, not unit vectors, and shall suppose to be unconnected by any linear relationship with each other. They are orthogonal in such a manner that if there be any other expression of the same form, the supposition of a quantity between these two quaternions is like that. So you can have one quaternion and you can have another quaternion that are related to each other by the I, J, and K. So the relationship between these two quaternions shall be understood to involve four separate equations between their respective constituents, namely the following: W goes to W prime, X goes to X prime, Y goes to Y prime, and Z goes to Z prime. Okay, so these equations are transformations. So W is transformed to W prime, X is transformed to X prime, Y is transformed to Y prime, and Z is transformed to Z prime. So in terms of demystifying Hamilton's quaternion, I am primarily interested in these four separate equations, which can be found down here in equation D. Okay, so here you can see he's invoking his rules. I squared equals j squared equals k squared equals -1. And here are the correct quaternion rules. I times j equals k, j times k equals I, k times I equals j. And the reverse, so j times I equals -k, k times j equals -I, and I times k equals -j. So these are the rules, Hamilton's rules of quaternions that, that he defined in the 1800s. Okay, so then he goes on to say, so he's talking about these products and how these are the negative of these. So he said, at first sight, it might seem strange and almost unallowable to define that the product of two imaginary factors in one order differs from the products in the other factor. But in fact, this is because quaternions are non-commutative. So when they are associative and non-commutative, so associative means you can reverse the pluses and minuses, but non-commutative means you cannot reverse I and j and get the same answer. Okay, so it will, however, it is hoped, be allowed that in entering on the discussion of a new system of imaginaries, it may be found necessary or convenient to surrender some of the expectations suggested by the previous study of products of real quantities, or even the expressions of the form x plus iy, in which I squared equals -1. Okay, so here he is writing I squared equals -1 and not I equals the square root of -1, okay? So these are the rules of quaternions that Hamilton defined in the 1800s. And here are the four equations that he wrote out that transforms one quaternion into another quaternion. So what I'm going to show you here is how to get from Hamilton's equations, which I copied and pasted and put here. I'm going to show you how to get from here to the 4x4 matrix version of quaternions. As you may recall, I define complex numbers as 2x2 matrices. So the square root of -1 is I and -I, which are under the hood are these 2x2 matrices. And this matrix is actually this matrix here with cosines on the forward diagonal and sines on the backward diagonal, and where the forward diagonal has the same sense and the backward diagonal has opposite sense. -I in a similar manner is the complex conjugate, so the negatives and positives get reversed, and so you end up with this matrix here. So this matrix here is a counterclockwise rotation in the xy plane about the z-axis, if that is your coordinate system, and this corresponds to a rotation in the opposite direction. So if this is counterclockwise, this is going to be a clockwise rotation. So what I'm going to do is I'm going to apply similar logic to the quaternions from the perspective of Hamilton's four equations. So what I wanted to be able to do was to extract the matrix values from these four equations directly. But there's a little bit of a problem here. For some reason, Hamilton felt compelled to put all the negative signs at the end of these equations. So he rearranged the equations to always put the negatives at the end. At least it looks like that's what he was doing. And I can't think of any good reason to do that other than the fact that maybe he thought it looked prettier. But this actually makes it impossible, not impossible, it makes it more difficult to see the matrix from these four equations. So what I did was I reorganized his equation so that all the w's are together, all the x's are together, all the y's are together, and all the z's on the left of these statements are together. Okay, so turns out these terms that are in color, these are the ones that I needed to rearrange to get these to line up nicely. Okay, so so now you can see, and let me go back to here, you can see now that I've got all my W's lined up, all my X's lined up, all my Y's lined up, all my Z's lined up, and now what I can do, okay, now what I can do is I can extract the quaternion matrix right from the equations, directly from the equations. Okay, so you can imagine that there's a little plus sign in front of all these W's. Okay, so I can basically just take the W's. So I've got, so what you want to do is you want to take the sign of the column and put the signs over here, and you want to take all the right-hand terms, the right-hand side of these terms, and put them into the matrix. Okay, so you can see we've got W, X, Y, Z, positive W, X, Y, Z. In the next column, we've got minus, plus, minus, plus, minus, plus, minus, plus. We've got X, W, Z, Y, X, W, Z, Y. Here we've got minus, plus, plus, minus, minus, plus, plus, minus, Y, Z, W, X, Y, Z, W, X. And in the final column, we have minus, minus, plus, plus, minus, minus, plus, plus, and Z, Y, X, W, Z, Y, X, W. So when you rearrange these equations to be the way Hamilton wrote it, for some reason he wanted the negatives at the end. I can think of no good reason to do that because it obscures the beautiful relationship between these equations and the quaternion matrix. This is a perfectly good quaternion matrix that you can implement on the computer, and you can use it to do rotations about an arbitrary axis in the XYZ. Okay, this is perfectly great, and I could get this from Hamilton's four equations directly, only I had to rearrange some of the terms. So as I said earlier, quaternions are associative but not commutative. So I can't replace a WZ with a ZW, but I can swap out, I can move around the positive and negative terms. I can rearrange them without affecting anything in terms of the quaternion. So this is the associativity I was talking about. So this, I want to place this one here, I want to place this one here, and I want to place this one here. And of course I want to place this one here, and this one here, and this one here, in order to get all my W's together, my X's together, my Y's together, and my Z's together. Okay, so again, I can think of no good reason why Hamilton would write. If Hamilton knew that under the hood of his equation was a beautiful quaternion 4x4 matrix that I can implement directly on a computer. Of course, he didn't have computers, so he wouldn't know that. If I were to go back in time and talk to Hamilton about this, I would be able to convince him to write his equations in his paper like this, because then someone like me could come along and pull out the matrix directly. I can write the matrix in a form that I can implement directly on my computer, and this is a beautiful thing. So here is the matrix that I have implemented in my computer program. I've taken the matrix that I found, that I extracted from Hamilton's equations in his paper, and I turned it into a matrix in matrix form. And in this particular matrix, I'm actually using column convention. So this is the column and this is the row. Okay, so this is column and this is row. Now, historically in my videos, I've used row convention. I often use row convention. One is not better than the other. The only reason I'm using column convention here is because it matches better with what Hamilton wrote. And so I wanted to go directly from Hamilton's equations to the matrix, to the matrix form in my program. So then I can take the W, X, Y, and Z and go W, X, Y, Z. I can take the X, W, Z, Y and X, W, Z, Y. So I can write my code exactly the same as the matrix that I extracted from Hamilton's equations. So where do I, j, and k fit into all of this? Well, as you may recall, Hamilton actually wrote the quaternion, the short form of the quaternion is w plus xi plus yj plus zk. Okay, and I wrote an r in here to remind us that the w component is the real component. So we have the real component and the three imaginary components of the quaternion. So you will notice that I corresponds to x, and you see the x in these locations in the matrix, and you see that j is associated with y, and y occupies these locations in the matrix, and you'll see z is associated with k, and z occupies these locations in the matrix. So here I have written I, j, and k in matrix form, and as you can see in the locations, so x is associated with I, and x occupies these locations in the matrix, and so I has ones occupying the matrix in these locations. And similarly for j, we put ones in the locations occupied by y. Okay, and we keep the signs the same as we have for y. And for k, we write ones in the locations occupied by z, and we keep the signs of the that we had in the original matrix where we have z. Okay, so these are the three matrices. This is I, j, and k in quaternion 4x4 matrix form. This is what I, j, and k look like under the hood. Okay, so clearly I, j, and k do not correspond to axes in a Cartesian coordinate system or in an alternate tri-spatial coordinate system, as the author of that paper was trying to indicate. Okay, I, j, and k are actually rotation matrices, and they rotate by counterclockwise by 90 degrees. Okay, so I rotates about the x-axis counterclockwise by 90 degrees, and j rotates counterclockwise about the y-axis, okay, 90 degrees, and k is a rotation about the z-axis by 90 degrees. And so so I is a rotation about the x-axis in the yz plane, j is a rotation about the y-axis in the zx plane, and k is a rotation, 90-degree rotation about the z-axis in the xy plane. So why 90 degrees? Why do I, j, and k rotate by exactly 90 degrees? And the answer to that is the same answer as we had for the complex numbers. So in the complex numbers, you have the square root of -1 is I and minus I, which are these two matrices where ones occupy the backward diagonal and have the opposite sense, and they correspond to these two matrices with sines and cosines, where the sine and the cosine is hard-coded to 90 degrees. So in a similar manner with the quaternions, I, j, and k, which have ones in these locations. So this is actually I with ones in these locations corresponding to a 90-degree rotation about the x-axis. And this is because under the hood of this matrix is this matrix here with sines and cosines that are hard-coded to 90 degrees. Okay, so here you can see the cosine of 90 is on the forward diagonal, and of course everyone knows that the cosine of 90 is equal to 0, and that's why we have zeros on the forward diagonal of this matrix. And similarly, we have on the opposite, on the off diagonal locations here, we have the sign of 90, positive sign of 90, negative sign of 90, positive sign of 90, negative sign of 90, and the sign of 90 is equal to 1, which is why we write 1s in these locations here, okay? And so this matrix here corresponds to a 90-degree rotation about the x-axis if we put x into these locations here. So if we write the 4x4 matrix as Hamilton did in his paper, then I would correspond to a 90-degree rotation about the x-axis. And so similarly, J corresponds to this matrix, where the 1s occupy the location where the y's are in this 4x4 matrix, and this corresponds to this matrix here. This could loosely be referred to as Euler's formula in quaternion form, because they are written in terms of sines and cosines. And again, here you see the cosine of 90, which is 0 on the forward diagonal, which is why we write zeros here. And the sine of 90 is 1, which is why we write 1s in these locations here. And so this is the matrix I would actually use in my code to do rotations about the y-axis. And of course, I don't have to hard code my angles to 90. I can use any angle that I want, okay? And similarly, K, analogously, K is also this matrix here under the hood. So here you can see that the 1s occupy the location of the z terms, here. And we've got the cos of 90 on the forward diagonal, which is why there are zeros on the forward diagonal. And we've got 1s in the backward diagonal here with the sines. And of course, the sine of 90 is 1, which is why we put 1s right here, okay? So this is why I, J, and K do exactly 90-degree rotations about their associated Cartesian coordinate system axes, x, y, and z, okay? This is, the reason is because under the hood of this is we are hard coding the angle. When we put 1s in these locations, we are hard coding the angle to be 90 degrees. And this is why I, J, and K are associated with 90-degree rotations, okay? Because they have the cosine and sine terms are hard coded to 90 degrees under the hood. So to prove that what I just said is true, I wrote a little computer program that takes a bunch of points and spins them about the various x, y, and z axes using the quaternion 4x4 matrix, okay? So if I want to rotate about the x-axis, what I do is I take the axis that I apply in the program and I set the axis equal to 1. So this is going to create a rotation about the x-axis only, okay? So as I said earlier, the shift does not have to be 90 degrees. I can set this to 90 if I want to, but it's not very interesting. So I'm going to set this to 10 degrees. So every time I do a rotation, it's going to rotate by 10 degrees, okay? And so by doing this, what I do is I go in and I set up my quaternion. I have a setup quaternion function, which is basically this function here. Where is my setup function? Okay, so here is the function where I'm setting up the quaternion matrix, and here is the code I showed you before. Okay, and so that is this function here. And what this is going to do, I'm not going to get into too much details, but what this is going to do is it is going to set up this function right here. It is going to set up this matrix, right here. Only it is going to be setting the 90 degree, instead of hard coding it to 90, I'm going to be setting it to theta, which is going to increment by 10 each time I click the button. So as I spin, each time I click the button, it's going to spin, and first it's going to be 10 degrees, then it's going to be 20 degrees, then it's going to be 30 degrees, etc. And it is going to be doing a 90-degree rotation about, it's going to be doing a rotation about the x-axis that is going to be increments of 10. So here is my code running here, and what I've done is I have added points. I have added some points in three-dimensional space, as you can see, and since I'm going to be rotating about the x-axis, so normally the x is to the right, the y is up, and the z is pointing towards me, but what I'm going to do is I'm going to point x towards me, and now you can see that it is rotating. We are rotating counterclockwise about the x-axis, okay? And so that is the first quaternion. This is the I imaginary component of the quaternion that is doing this. So now what I'm going to do is I'm going to go back to the code, and I am going to change this to the y-axis. So now we're going to rotate about the y-axis. Now we're going to be using this quaternion matrix, and this is going to be, instead of 90 degrees, I am incrementing by 10 degrees each time I click the button. So this is going to be doing rotations about the y-axis. So here are my points again, and so now we've got positive x pointing to the right, positive y pointing out, and positive z pointing towards me. So what I'm going to do is I'm going to rotate my coordinate system so that y is pointing towards me to make it easier to see that I am in fact rotating about the y-axis, counterclockwise about the y-axis every time I click the button. And for completeness, I will do the z-axis. So when I set this equal to 1, what this is going to do, it is going to be placing a matrix that looks like this into the rotation matrix. The rotation matrix will look like this, only the angles will be theta, incrementing by 10 degrees each time I click the button. And so this is going to be rotating about the z-axis. And so here are my points again, my random points in the 3D coordinate system, in the XYZ Cartesian coordinate system. And now I have z pointing towards me, which is where I want it, because it is easier to show you that I can rotate about the z-axis. So now I'm rotating my points about the z-axis only. So now what I'm going to do is I'm going to do one more thing. What I'm going to do is I'm going to set these all equal to 1, which means it is going to rotate my points about an axis that is not x or y or z, but somewhere in between. Okay, so let me rebuild this. And this, of course, is the beauty of quaternions, is that you can rotate points about an arbitrary axis. The axis doesn't have to be the x, the y, or the z. It can be about the x, the y, and the z. Okay, so now when I spin my points, you can see that it is spinning about an axis that is not x, y, or z, but it is rotating about. So here you can see, let me bring this up and maybe make it a little bit bigger. You can see that this is rotating about an axis that is sort of in between x, y, and z. And this is the beauty of quaternions. It allows me to do this. So I'm going to spin this around, and you can see that it is spinning about an axis that is not x, y, or z. That's really hard to see because this is 3D. It's hard to see because we're painting everything onto a 2D plane. But when I orient my axis to be, I'm going to try and orient it almost exactly so that x, y, and z are pointing, so that the axis I think it's rotating about, which is this axis here, is exactly in where, so that you can see the rotation. Now it's really hard to do, but you can clearly, there we go. Clearly you can see that we're rotating all these points about an axis that is not x. So x is not pointing towards me, y is not pointing towards me, and z is, sorry, x is not pointing towards me, y is not pointing towards me, and z is not pointing towards me. Some arbitrary axis is pointing towards me, and so I am spinning my points about that that arbitrary axis. Okay, But in order to do a rotation about an arbitrary axis, as opposed to just around x, y, and z separately, we need to use this matrix here. Okay, so I refer to this as Euler's quaternion. This is analogous to Euler's complex number, where you have sines and cosines in all the entries in the matrix. And so the difference here is that now we need to distinguish between how much of the x we are using, how much of the y we're using, and how much of the z we're using. So we're multiplying each entry by a fraction of the x-axis, a fraction of the y-axis, and a fraction of the z-axis. And this allows us to do a rotation about an arbitrary axis by an arbitrary angle. But there's a catch. There's a catch when we want to do rotations in the 3D Cartesian coordinate system using this matrix here. So in order to do a proper rotation in the 3D Cartesian coordinate system using the 4x4 matrix version of Quaternions, we actually need two matrices. We need the quaternion matrix and we need the complex conjugate. And so you will see that the complex conjugate, everywhere there is a sine function, gets negated. And so if it's negative here, it's positive here. And if it's positive here, it's negative here. And the forward diagonal does not get changed in the complex conjugate. It is still the cosines on the forward diagonal as usual. So then what we need to do is we need to take a Cartesian, we need to take a quaternion point, which is a point in the Cartesian coordinate system with the first entry set to equal to 0. We need to take this 1x4 matrix and multiply it by the quaternion matrix, and we end up with a new point, QP prime, and then we need to multiply it by the complex conjugate in order to get QP prime prime. And so you'll also notice that we have each time, so the first time we do the multiplication, we pass in half the angle, okay? And then when we do the complex conjugate multiplication, we pass in half the angle. So the transformation has to be done in two parts when you use quaternions. This is true whether you're using matrices or some other algebraic method for implementing quaternions. You need to do this first, and then you need to do this second. And the other complication is when you do this multiplication, you need to post-multiply the point, and then when you do this multiplication, you need to pre-multiply the point. And I'll show you what that looks like in my code. So when you're doing matrix multiplication, you can either multiply the matrix by the point, or you can multiply the point by the matrix. Okay, so the order that you do this multiplication actually, and so to get a proper rotation, you need to pre-multiply this point by this matrix and post-multiply this by this matrix, or you need to post-multiply this point by this matrix and pre-multiply by this matrix. If you don't do that, then you get really strange results, which I will show you. I'll show you what happens. I think I'll show you what happens when you don't actually do the rotation in two steps in the 3D Cartesian coordinate system. So normally what I do in my code is I set up my quaternion matrix, I set up the matrix here, and then I set up the complex conjugate matrix here, and then I multiply the matrix by the point and get my result, and then I multiply with the result by the conjugate matrix and get result 2, and that's what I plot in my code. But what I'm going to do here is I'm going to enable using the whole angles, and what that is going to do is it is going to, let me just start the build here. What this is going to do is it is going to, I'm going to use the whole angle. I'm going to bypass the conjugate step, and I'm just going to multiply my point by this matrix, and I will show you, once this is done building, I'll show you what happens. Okay, so now let's run the program. Okay, I'm going to add my points, and then I'm going to spin the point. So what I'm going to do first is I'm going to show you the rotation about the axis that we're rotating, which is the arbitrary in between XYZ axis. You can see it looks like it's rotating nicely about the axis, okay, but then when we look at this from the side, you will see that it is actually squishing. It is not conserving the distances between the points when I rotate, and after 90 degrees worth of rotation, all the points are in the same plane. Okay, so this is what happens when you don't use the complex conjugate, when you don't do your transformations in 2 steps. Okay, so this is actually kind of cool, but this is not what we want. In computer graphics, we don't want our points. We want the relationship between the points to stay consistent relative to each other. Okay, so I'm going to put things back the way they were. Okay, so I'm going to rebuild my program using the half angles, using the 2 matrices, this one, the normal rotation matrix, and the complex conjugate. Okay, we'll let this build. And then I'll run the program. And let me see, I'll add my points. Okay, and now you can see that the spinning is happening correctly. So when I look down the axis of rotation, it's spinning correctly. And when I go off axis, it is also spinning correctly. The relationship between the points isn't changing. And so this is the complication with using quaternion matrices, or using quaternions in general for doing rotations in 3D graphics. You have to split it up. Okay, you have to split up the multiplication into 2 multiplications using the original matrix and the complex conjugate, and you have to pre-multiply the first point, or post-multiply. I actually post-multiply. I post-multiply the point with the matrix, and then I pre-multiply the result with the complex conjugate to get my final XYZ coordinate. And so this is what quaternions are for. This is what quaternions do. Okay, quaternions are really fascinating. I've been fascinated with them for years. And so this explanation, this is an explanation of quaternions, is fairly straightforward. And I was able to get there directly from Hamilton's equations from his paper. Okay, I was able to look at Hamilton's equations from his paper. And because I knew about the matrix form of the quaternion, I was able to rearrange Hamilton's equations, as I showed here, where I had to take these terms and rearrange them so that all of the w's on the left of each term line up, all the x's, all the y's, and all the z's line up, and I was able to extract the quaternion matrix right directly from Hamilton's paper, okay, from the 1800s. So hopefully you can see why I don't agree with the premise of this paper that quaternions form some sort of alternate coordinate system or trispatial geometry where I, J, and K are some sort of unit vectors. Okay, I, J, and K are definitely not unit vectors by definition. Okay, in fact, I can prove, as I showed you in this video, that I, under the hood, I is in fact a rotation matrix, where I is a 90, I, J, and K are rotation matrices, where I is a 90-degree rotation about the x-axis, J is a 90-degree rotation about the y-axis, and K is a 90-degree rotation about the z-axis when using this quaternion matrix here with the W, X, Y, Z defined like this. So obviously I am not rejecting the foundation of the very concept of quaternions, and I am in fact embracing it. But there is one more thing we need to look at, and that has to do with this -1 right here. So let's have a look at these 3 situations right here. So we have the real numbers where there's no imaginary component, and so there's no number you can square to get a negative number. Okay, so then we have the complex numbers, which are 2-dimensional numbers where you do have a concept of I, where you do have a number that you can square to get a negative number. So in complex numbers, -1 is actually equal to this matrix here. Okay, so this is I squared equals minus I squared equals -1, but not -1, not the real -1, but the complex -1. Okay, so I squared is equal to minus I squared is equal to complex -1. Okay, so complex I squared is equal to complex minus I squared is equal to complex -1. So in quaternion numbers, where the numbers are 4x4 matrices, where they're technically four-dimensional numbers, we have I squared is equal to J squared is equal to K squared is equal to -1. Okay, so we have I squared, as I showed you, this matrix here is the I matrix, so I squared is equal to J squared, this is the J matrix, is equal to K squared, which is this matrix here. When you square this matrix, or when you square this matrix, or when you square this matrix, you get this matrix here. So this is -1 in quaternion numbers. Okay, this is -1 in real numbers, this is -1 in complex numbers, and this is -1 in quaternion numbers. And so in quaternion language, I squared is equal to quaternion -1, not real -1. Okay, in complex numbers, I squared is equal to complex -1, not real -1. Okay, so when you say I squared equals -1, we have to be very clear about what we're saying. Okay, so I squared, I is a complex number. I itself is a complex number, it's not a real number, obviously. So when we say I squared in complex numbers, we get complex -1. This is complex -1. And similarly, when we are in the domain of quaternion numbers, I squared is equal to quaternion -1, not real -1. Okay, so I squared is equal to quaternion -1, and J squared is equal to quaternion -1, and K squared is equal to quaternion -1. In general, we need to think about this a little more clearly. We need to distinguish between real numbers, complex numbers, and quaternion numbers, and we need to be very clear that complex I squared is equal to complex -1, and quaternion I squared is equal to quaternion -1, not real -1. Okay, so when we do things algebraically, we might be inclined to say I squared is equal to real -1, where quaternion I squared is equal to real -1, but under the hood, in reality, I squared is equal to quaternion -1, and J squared is equal to quaternion -1, and K squared is equal to quaternion -1. Okay, so I just wanted to point that out. This is a sort of a insight I had while I was making this video, and so I think this is it is important to distinguish between whether we're talking about real numbers, complex numbers, or quaternion numbers. Truthfully, I wish I was around when Hamilton came up with his idea on quaternions, when he wrote his papers. Okay, here's one paper he wrote, and here's another paper he wrote, where he wrote his equations. Okay, because if I was around when Hamilton was defining his equations, this equation here, I would kindly ask him to rearrange his equation to look more like this, so that all of the w's line up, all the x's line up, and y's and z's line up on the left hand side of these terms, so that we could more easily extract the 4x4 matrix version of quaternions. Now, I'm not entirely sure he even knew about the 4x4 matrix version of quaternions, because I don't think he ever wrote about them, and at least I have never seen any paper where he's written about them. Okay, and the other thing I would want to tell him, I would say, hey dude, there's actually 3 different kinds of -1s. There's a real -1, and there's the complex -1, and there's the quaternion -1. And so you might want to rewrite your equations like this. When you're talking about complex numbers, you would want to maybe say I sub z squared is equal to -1 sub c, which corresponds to this. And you might want to say I squared q is equal to j squared q is equal to k squared q is equal to -1q, where -1q is this matrix right here. Okay, so you know, if I could go back in time and talk to Hamilton, that is likely what I would want to say to him. Okay, so I would have something to say to William, the famous Sir William Rowan Hamilton. If I could go back in time and talk to him, I would definitely have something to say to him. Okay, so this video is getting quite long, so I'm going to end this video right now before I think of more things to say, and then I will sign off. And of course, as usual, I will be back.